it's a pleasure to have here Professor Armando Solar-Lezama. He's a specialist in the topic of this workshop. He's a professor at MIT, where he leads the computer-assisted programming group. And he's also the associate director and COO of the Computer Science and Artificial Intelligence Lab, CSAIL. He also leads the NSF-funded expeditions in computing project, Understanding the World Through Code, which aims to develop neurosymbolic learning techniques for the purpose of accelerating scientific discovery. And I guess more or less this last topic is going to be the main topic of the talk of today. So again, thanks Armando for sharing your knowledge and your time with us. And it's a pleasure to have you as an invited speaker for this event. Thanks.
Thank you. Thanks a lot. It's really great to be here. Would be great to be able to be in person, but it's also nice to actually not have to fly. So let me share my screen here. Okay, and so you can see my screen now. So my background actually is.
Oh, sorry. Now it's there. Sorry to.
All right, perfect. Yeah, so my background is actually in programming languages and programming systems, and it was in programming languages that for many years now we have been working on this problem of program synthesis and this question of how do you take behavior constraints about what a piece of code should do, together with structural constraints about how the program should look like, and how do you bring them together to actually generate a piece of code that does what you want, that uses, for example, the building blocks that you told it to use. And originally, our goal with this kind of technology was to help software developers. And so from that perspective, there have been some success stories in this field. For example, data structure manipulations is one area that is becoming pretty mature. Modern program synthesis tools can actually do a really good job of generating even fairly complex manipulations to pointer-based data structures. Another area that is really considered a success story in the program synthesis field is data wrangling and data manipulation in general. So flash fill, for example, was really a landmark piece of work from Sumit Gulwani and his team in demonstrating the use of program synthesis in this very, very important domain. But one of the questions that we have been really interested in is, could we apply these techniques beyond programming, beyond software engineering types of applications? And so actually going all the way back to 2010, there was this paper that was actually very influential by Susmit Jha and Sumit Gulwani and Sanjit Seshya and Ashi Tawari. And in this paper, one of the things that they showed was that even though normally people think of program synthesis as, I'm a user, I have a specification, and I want to generate a piece of code, an implementation that implements that specification. What they showed was that you could also do it the other way around, and you could actually leverage these techniques that allow you to search for programs that satisfy some structural and behavioral constraints. And you could use them to start with an implementation and essentially reverse engineer the specification. And in the case of that paper, they actually did it first by reverse engineering pieces of code that came from computer worms and exploits that are often purposely obfuscated to hide their meaning, and they showed that you could actually reverse engineer a high-level specification by observing their behavior. And so it turns out that this idea has actually proven to be really powerful, because what it allows you to do is it allows you to leverage program synthesis techniques in situations where you have some artifact in the world that you're trying to understand, and what you're trying to do is to come up with a higher level model of it. And so in our own work, we have done this, for example, for large software frameworks. One of the things that has traditionally been a roadblock for applying program reasoning techniques to very large code bases is that they generally require a model of the underlying framework over which your code is written. For example, if you have an Android application, your tool needs to understand what the Android framework is going to do, how it's going to react to certain things. So in this paper, already a few years ago, we showed that we could actually reverse engineer certain aspects of the framework that would then be useful for driving some program analysis. A little bit more recently, we actually showed that you could do this even in a space that has seemingly nothing to do with software. So for example, we showed that we could actually take solid models of solid shapes, essentially just a point cloud that describes a lot of points in the surface of this shape. And from that, reverse engineer the set of geometric operations that could actually produce the shape in question. And so this was really exciting because it was really applying these techniques. We actually did this leveraging our sketch synthesis infrastructure, and we were able to do this in a domain that, again, seemingly has nothing to do with software engineering. And in fact, in more recent work, Kevin Ellis, in collaboration with Josh Tenenbaum and myself, and actually more recently also Tim O'Donnell has been collaborating with us in this project. We've actually been looking at the problem of, can you reverse engineer language morphology rules, for example, from data, using essentially these very traditional program synthesis techniques. I guess now I'm allowed to call them traditional because they're more than 10 years old. But all of this was done using these SAT solver-based program synthesis techniques that we had developed originally for the purpose of helping with software development. However, as we started trying out these program synthesis techniques in a variety of domains, what we also learned is a lot about their limitations. Existing techniques for program synthesis were very good at synthesizing very small pieces of code on the order of less than a dozen lines of code. And the problem is that you're doing this combinatorial search problem that is actually quite challenging. And for every one of these very exciting projects, it actually took, more than a year of graduate student time, of really carefully crafting the search space, the space of programs that the synthesizer is going to consider, so that on the one hand, it's big enough to actually find all the programs that we want to find in this domain, but also so that it's small enough that you don't, that your search does not blow up. And so as we started working on this and started running into the limitations of these traditional techniques, we started really looking more carefully at how we could better incorporate learning into this process. And so today I'm going to talk about a couple of projects where you can see the intersection between some of these more traditional program synthesis techniques with more learning-based approaches in ways that allow us to do things that we couldn't really do either by using just the traditional program synthesis techniques or by using just off-the-shelf deep learning strategies. So what we're after here is really a I guess a synthesis of traditional programming languages, symbolic reasoning techniques with these optimization-based learning approaches that allow us to get some of the benefits from both worlds. And so one effort that I want to talk about is actually this effort that was led by Kevin Ellis together with a large team of collaborating students. And this was supervised by Josh Tenenbaum and myself. And this project actually arose from the observation that for many of these problems, a big challenge was handcrafting the right high-level domain-specific language to describe your problem. What you really want is you want a domain-specific language where the programs that you're looking for can be described in a very concise way. And so the idea is that, in traditional program synthesis, we're really good at this problem of here's a bag of components, here's a set of building blocks that you can use, and your goal is to assemble them together to come up with a function that actually does what you want. But the components are always assumed to be given. Now, that begs the question of where do these components come from, and could we actually learn them from scratch? And so we actually tried this in a variety of domains. And one of the domains that I will use here to illustrate some of these ideas is this domain of logo graphics. This is kind of a very classical AI domain where the goal is to generate little programs that draw these somewhat intricate shapes. And the idea was to see whether we could learn these programs starting with a very simple low-level language, right? So the idea here is going to be that you want to start with just a low-level language that in principle could express all of these programs. And in this case, the language basically has the ability to move the pen. You have pen up, pen down command. You have basic loops. You have basic arithmetic. And so the problem is if you try to paint some of these more intricate patterns just using this language, the programs that you have to write can end up being quite large, larger than what traditional synthesis techniques might be able to do. And so the idea was to actually generate an algorithm that is able to infer those components from scratch. And our starting point was actually some prior work from Josh Tenenbaum's group that had been looking at this problem and had an idea for essentially a wake-sleep algorithm, where first you try to solve as many problems as you can, and then you try to identify common subcomponents of those solutions that you can turn into programs, right? So the idea is you start with a large body of synthesis problems. And so you're trying to synthesize as many programs as you want. And one of the things that you want of these synthesis problems is you want to have a range of difficulties. You want to have simple programs and more complicated programs. So in the beginning, you're probably only going to be able to solve the simplest of these problems. But then the idea is that you can take these problems and you can identify common subcomponents of these programs to build as components. Now, there are two challenges in doing this. One challenge is that the programs, even if logically speaking, they're doing similar things, they might not actually be syntactically similar in a way that you can identify a common subcomponent. And the second problem is that as you add more components, yes, you're able to generate more complex programs with small numbers of commands, but also your branching factor of your search grows because now you have more components. And so what made this project interesting were two ideas that allowed us to address both of these issues. And the first idea was to use symbolic techniques and to actually take programs that looked very different, but logically speaking were actually similar, and to extract those common subcomponents, even though the programs didn't look similar. And the other idea was to actually build these models that would allow us to guide the search for these programs so that you're not just searching the space blindly. And so by generating this language using these symbolic techniques together with learning these models, we could actually do something that turned out to be quite effective. Now, finding these common subcomponents turns out to actually be a tricky symbolic problem in itself, right? Essentially, if you look at, let's say that I have some list problems, right? That I'm trying to figure out from some examples what the program is, right? And let's say that from these two examples, I actually come up with these two programs, and the actual project works in a Lisp-like language, but in this case, I'm just showing some Python code just to give people a sense of what of how this works, right? So the idea is you have these two programs that, logically speaking, they're doing very similar things. They're iterating over a list. They're doing this modification for every element, and then they're returning the list. But syntactically, they look very different. They iterate in different ways. They are doing a different arithmetic expression. If you look here for common sub-expressions between these two, you're not going to find many. But what we show is that you can leverage data structures based on the data structures that are nowadays often used for representing version spaces in a very compact way. And you can use these data structures to very compactly represent very, very large spaces of possible refactorings for your original program. And so the idea is that if you're able to take this original program and expand it into this very, very large space of possible refactorings in a way that allows you to, within those refactorings, identify common subcomponents, what you can find is you can actually find a refactoring that exposes the commonality between these two pieces of code. And so in this case, what you have is that you can refactor both of these programs in a way that exposes the enormous similarity between these two different approaches, and in a way that you can directly pluck out these very substantial common subcomponent that now can be incorporated into your library as a new building block that can be used in order to generate that code. And so what we see is that by doing this in an iterative manner, the system is actually able to discover some really interesting subcomponents. So for example, in this drawing domain, the system is actually able to find subcomponents that can draw circles and semicircles and spirals and polygons. But more interestingly, it's also able to discover these higher order components. For example, that you give them a function to draw a shape, and then this component uses that function to draw this radially symmetric version of this shape, essentially by making these copies of this shape, right? So it's able to learn these higher order components that can then be used to actually generate these very substantial programs. And so by building this hierarchy of components at every iteration, building new components on top of the old ones, it's able to actually learn a language that can generate the target drawings very, very efficiently. And so it never actually has to learn very large programs. At every step, it's trying to solve as many problems as it can with relatively small programs, and then using those to find the new components that it can use to generate new programs. Maybe I shouldn't say relatively small. I mean, these are just small. But they can do very substantial things because these components are defined hierarchically. And for many of these programs, if you were to expand them into the code in terms of the low-level language, these would actually be very large programs, much larger than what we can discover. Now, I want to show you a very different example from a different kind of approach for, just like this previous project is able to combine deep learning and the ability to learn how to search for programs with these fairly sophisticated symbolic reasoning in order to find you programs that do interesting things. In the case of this project, what we have is a very tight coupling between symbolic search and numerical optimization. In this case, with the goal of finding controllers that actually generalize inductively. So this work was led by Jivana Inala, and it was in collaboration with Osbert Bastani and Zena Tavares, together with myself. And so the motivation for this project is that in a lot of cases, you find the need to discover controllers that do periodic behavior, right? In particular, a big inspiration for us was this parallel parking problem that you see on the right, where oftentimes if you're in a really, really tight parking spot, you have to go back and forth and back and forth and back and forth a number of times before you can actually escape. And this actually requires an ability to generalize beyond the examples that you saw. So, for example, what we would really like to see is that if you train a system on a handful of examples, some of them that require just one back and forth step, some of them that require 2 back and forth steps or 3 back and forth steps, what you'd hope is that the system actually learns the general strategy, so that even if it's in a really, really tight parking spot, right, the one that requires going back and forth many, many more times than what you've seen before, you would expect that the system actually has learned the pattern and is able to do this. But what you find is that if you take a more traditional reinforcement learning approach, and you train it in these different scenarios, you can actually find a policy that works really well for every one of these scenarios. But it works in sort of a very ad hoc way. You can see that in the trajectories on the left, you don't see the regularity that you saw or that you would have liked to see. It somehow found a way to come up with a policy that escapes this parking spot. But this is not a policy that has caught on to the repetitive nature of this task, and therefore is not one that generalizes very well to new situations that require many more back and forth steps. And indeed, what we see is that if you go to these new situations that were never seen in the training data, the policy fails pretty badly with lots of collisions. And so how can we learn a policy that actually inductively generalizes? And the key idea is that we want to learn a policy that essentially takes a form of a hybrid controller. At every step of the process, there is a continuous controller that defines how you're going to behave when you are in this mode. But you also have these predicates that, when those predicates are satisfied, they trigger a transition to a different state with a different continuous function. And so in this case, the nature of the state machine is what gives you your repetitive behavior. The fact that you're switching back and forth between these states until you get to this final state that finally takes you out of the parking spot. And so the challenge is, can we learn policies that look like this? And in particular, this means not just learning the continuous parameters of these individual states, it also means learning the predicates, the specific predicates that are going to transition you from one state to the other. And it actually also means learning the transitions themselves, figuring out exactly where these edges are going to live. And so what this paper was all about was our algorithm for actually doing this. And the high-level idea here is essentially a teacher-student algorithm. The idea is that we start with a teacher, which is completely numerical. It's based entirely on numerical optimization. And the goal of the teacher is just to learn some loop-free policies that maximize the reward. In the case of the parallel parking, they get to the goal without collisions, right? And so each one of these policies, essentially what it's looking for is just a trajectory that from some randomly selected initial state is able to satisfy the task. And so what you have is, at every step in this process, you have a set of continuous parameters that you have to optimize to determine what needs to happen in that step. So this is just a straight line policy. It's essentially just a plan for this particular situation. And then we have a student, right? And the student is trying to learn a state machine policy that imitates these loop-free policies. And the student is actually going to be neurosymbolic. It's learning the guards, it's learning the structure, it's learning these individual policies, but it's trying to imitate what the teacher is doing. Now, the challenge is that the teacher didn't know that the student was actually going to be trying to do this. And so the teacher might have learned a policy that was not very conducive for the student being able to follow it. So the idea is the teacher learns these sequence of actions. Every action is conducted for some amount of time. And the first thing we're going to do is try to group these actions into concrete modes of behavior. Essentially, what we're trying to do is cluster those actions into a small set of modes. And we're going to then try to learn the transitions using more traditional program synthesis techniques to learn the appropriate transitions from one of these modes to the other. But the interesting part comes later when generally, if you just try to do this once, it's not going to work very well. But now, this is where the adaptive teaching part comes in. We want to go back to the teacher and say, okay, you learned this policy. Now, I want you to learn a new policy where in addition to trying to maximize the reward, we also want you to try to imitate the student as much as possible. And so the idea is that it's not just the teacher pushing the student to behave in a particular way. The teacher is then looking at what the student did and trying to adapt its strategy in order to be a better teacher, in order to try to meet the student in the middle and be more like the student. So that in the next iteration, the teacher learns policies that hopefully are easier to turn into state machines. And so by doing that, what you find is that you're able to learn these policies that actually generalize much better, even to these situations that are very far out of their training regime. And so what you find is that if you just look at the training set, right, actually our policies do, just as well, in some cases, even a little bit worse than the policies that you train using RL. But as soon as you go to a test set that has some examples that look really different from the examples that you trained on that require this inductive generalization, you can see that the performance of these state-based policies holds up much better than the performance of the policies that were learned through reinforcement learning. And so these are just two examples of the kinds of strategies that we can use to combine together these different modes of reasoning. And as was mentioned in the beginning, we actually now have started a new NSF-funded project where we're looking at leveraging some of these techniques for the purpose of scientific discovery, where the idea is to leverage some of the advantage of these neurosymbolic methods, such as the ability to be more interpretable, the ability to incorporate more domain knowledge about particular domains, and the ability to potentially analyze the artifacts that come out in order to do more than just make predictions, but to actually be able to really understand a variety of natural phenomena, ranging from RNA splicing to organic chemistry, to cognitive science, to even large-scale computer systems. And so with that, I think this is probably a good time to stop, and I'll be happy to answer questions.